Welcome to Module 3 of our Belt Analyst webcast series. This module is evaluating results. My name is Mark Hallspaw. I'm the president of Overland Conveyor Company, and we'll be working you through this particular webcast today. We are assuming in this module, evaluating results, if you already have set up a Belt Analyst program file, all the particular belt conveyor information has been input. We've gone through that in previous sessions, and in this session we'll talk about evaluating the results and looking at various what-if scenarios. We're going to discuss volumetric capacity, first of all. Secondly, we'll talk a lot about power and various friction factors and determining a design range to look at, including all pertinent loading conditions. And then thirdly, we'll be looking at the various components and discussing the evaluation of pertinent output versus input values. As we open up our program, Belt Analyst, you'll see this may look a bit different than the version you're using. This happens to be version 10.3, which was released in October of 2011. And if you're a version 10 user, you can upgrade to this program by sending a request to us. First thing we're going to talk about here is volumetric capacity. Volumetric capacity is shown here in the cross-sectional area, first of all, and is based on the width of the belt, the belt speed, and the tonnage capacity up here in the upper right-hand corner. It is also based on the degree of idler angle and the idler configuration, and most importantly, in the material characteristics. So in this case, we have selected an aggregate at 1,400 kilograms per cubic meter density and 20-degree surcharge angle. And this is what this particular calculation is based on: the width, speed, load, idler configuration, and this material property. What we want to make sure here is that if you're doing an existing conveyor and you have existing parameters, then you're just going to get a calculation and you really don't have too many decisions to make. If you're dealing with a new application, we're going to evaluate this particular set of conditions to see whether the conveyor is properly utilized from a volumetric standpoint. A few things we want to make sure of is that we're not overloading the conveyor volumetrically, so 100% would represent the belt filled as much as you would ever want to fill it, and typically designers want to stay in the 80 to perhaps 85% range of what the manuals would consider fully loaded. In this case, we're at 73%. It's referenced here. It's also referenced here at the bottom in our dialog box. The important thing here for us to be aware of is the material density and the surcharge angle, and we want to actually underestimate those values. In this case, we're at 73% of what we consider to be fully loaded. If I actually increase the material density, you'll see the percent loaded actually goes down, which is good. If I decrease the material density, the cross-sectional area actually increases, because the capacity is based on the tons per hour of throughput. So if we decrease the density, the percent loaded goes up, and we're now at 78%. And likewise, if I decrease the surcharge angle, you see in the graphic the material appears to flatten out because the angle is smaller, and therefore we're closer to what we would consider fully loaded. If I decrease that to 10, we're at almost 100%. We're at 93% fully loaded. The other thing here that needs to be evaluated as I put these things back to the starting point is the edge distance right here. is the distance between the edge of the belt and the edge of the material, and in this case 156 millimeters. We want to make sure that our biggest lump size, in this case 25 millimeters, is not, if that largest lump size rolls to the edge of the belt, that it's not going to fall off the edge. So if we were carrying a 300 millimeter size lump, then half of that lump would be theoretically extended over the belt and could easily fall off. Therefore, we would probably want to reduce the capacity on the conveyor so that the edge distance is more in line with the size, maximum size of the lump. So in this case, in this case we might want to reduce the overall capacity to 1,000 tons per hour so that these large lumps don't have the capacity of falling off the conveyor. Next thing we're going to look at in our evaluation is our power calculations. This particular example, we have a 400 kilowatt motor, and the demand power in this particular snapshot in time is 258 kilowatts. So the first thing we're going to do is look at the loading of this particular conveyor and see if there's other loading conditions which might actually require higher or lower power requirements. We certainly know, and again these are snapshots in time, we certainly know that if we take the load off of this conveyor and run it at zero tonnage, that our power is going to go down. And in this case it's going to take 150 kilowatts to run this thing fully loaded. It's usually a pretty good idea to look at these conditions and see if there are any problems with an empty case, and there may be in terms of vertical curves, and you can see here that there's some red that showed up, so there's something that might be required us to look at there in vertical curves. And I'm going to reload the conveyor all the way up, fully loaded conveyor, 352 kilowatts. But let's look now in this particular profile. It's not straight, there's some ups and downs, so we're going to have some other conditions that we might want to consider, and the program is well suited to evaluate some of these conditions. For instance, one of the things that we might want to look at under edit, the edit loading carry side of the conveyor, we might want to automatically look at a load on load off condition and see if there's a condition here that might we'll wait for it, there it is, that might require some additional power. I'm going to put a 1 second delay in there. When I hit play, you're going to see the material start loading on the conveyor gradually from tail to head, and you see the tension diagram changing and all the calculations being updated in every calculation. So we can sit here and look for red things to happen to indicate potential problems, and you can see there are load conditions here that are potentially worse than that fully loaded condition. I'm going to do that again. We'll play through that again, and I'm actually going to stop it when we come to one of these conditions that turn red. And we can see here as we start to load off, here's a couple of red conditions, and if I stop it and look at it, you can see the power requirements in this condition has exceeded our nameplate power, and also our belt tension has exceeded our belt limit. So this is a very quick way to evaluate a whole bunch of loading conditions, and we can make adjustments to our power and our belt if necessary, or at least we can make a decision whether this is something we need to be concerned about. Obviously in this case, this is a very real case, and if the conveyor stopped in this condition, we have to make sure we have enough power to start it back up. So I'm actually going to turn this off and go to my power and say, yeah, I probably need to have 600 kilowatts of power there for that load condition. Likewise, I might want to look at some very extreme conditions, and in the same edit loading carry button, I can look at inclines loaded only, and again the power just barely exceeded my 600 kilowatts, and my belt tension also exceeded my belt limit. So I may make the decision here to increase my belt tension and and I may or may not decide to increase my kilowatts. This is a very unusual condition and a very temporary condition, and we may decide the motor has the ability to work into its service factor for the 3 seconds that this might occur. So very quickly we can adjust loading conditions and find the worst cases, and it's very important to make sure you do that anytime you have a conveyor that has multiple angles.